Hello everyone and welcome to this week's OpenGL 3D game tutorial, and this week we're going to be implementing normal mapping. Normal mapping is a way to make your objects look a lot more detailed and realistic without having to actually increase the complexity of the models. It can be used to make completely flat or smooth surfaces look bumpy and detailed like this. If you remember back to the lighting tutorials, the lighting on an object depends on the object's surface normals. If you take a very simple object like a cube, then the normals on each surface will be pointing in the same direction, and the lighting on each side of the cube will look very flat. If we used a much higher polycube model with lots of little bumps and indents, then the normals would be a lot more varied like this, and the lighting would therefore show off these details in the surface. What normal mapping allows us to do is to use a low poly model with flat surfaces like this, but it allows us to pretend that it's actually a highly detailed model by using the sort of normals that would be caused by a bumpy and detailed surface. By using these fake normals in the lighting calculation, the light acts on the surface as if it were uneven and rough, even though it's actually completely smooth. These fake normals have to come from somewhere though, and that's where the normal map comes into play. A normal map is a texture which specifies the surface normal that should be used for every single point on the object's surface. The normals are stored as colours in the texture, so to get the normal at a certain point on the object, we would sample the normal map at the relevant point, and that would give us an RGB colour, where each value is between 0 and 1. However, the XYZ components in a normal vector can be between -1 and 1, so we need to do a simple conversion here on the colour values, and we did this a few times in the water tutorials. So by multiplying the RGB values by 2 and then subtracting 1, we get 3 values between -1 and 1, which can now be treated as the X, Y and Z components of a 3D normal vector. So by mapping the normal map to an object just like we do with any other texture, we get a 3D vector representing the fake normal for every single fragment of the model. So right now, normal mapping might seem like a fairly simple feature to implement. You just have to sample the normal map texture in the fragment shader and then use that normal in the lighting calculations. However, it's unfortunately not quite that simple. Take this object here for example. Imagine that you then use a normal map like this, which indicates that all of the normals should be pointing directly out of the surfaces of the object, so that the faces of the object all appear completely flat, like this. However, if you treat the normals extracted from the normal map to be in world space, then they'll all be pointing upwards in relation to the world. If you treat them as being specified in relation to the object's origin, then they'll all be pointing upwards in relation to the up direction of the object, which again isn't what we want. The normals in a normal map are actually specified in something called tangent space, so they're specified relative to the original normal of each face. Take the top face here for example. The original normal vector was pointing in this direction, so that is now the up direction for the tangent space of that face. So all of the normals from the normal map on this face will be pointing upwards in tangent space. For this face on the right here, the original normal was pointing in this direction, so the normals from the normal map on this face will also point in this direction because that's the upwards direction in tangent space for that face. And it is of course the same for all of the other faces. So the normals in a normal map are represented in tangent space, but our lighting calculation is done in world space, where the camera position and the light positions are all in relation to the world. For our lighting calculation to work, everything needs to be calculated in the same space. So we have two options here. Either we can convert the normals from tangent space to world space and then do the lighting calculation in world space, or we can convert everything else, such as the light direction and the camera direction, to tangent space and then do the lighting calculation in tangent space without having to change the normals at all. And we're actually going to use the second option here because transforming the normals would have to be done in the fragment shader, whereas transforming the camera and light directions can be done in the vertex shader. So we need to convert the camera and light direction into tangent space, and to do that we need to create a matrix that can transform vectors into tangent space. To do that we need 3 vectors that define the tangent space, so we need the up vector, the right vector and the forward vector, basically the X, Y and Z axes of the tangent space. As I've mentioned already, the up direction in tangent space is just the original normal of the face. The right and forward vectors can actually be pointing in any direction as long as they're perpendicular to each other and perpendicular to the up direction, but whatever directions are chosen need to be consistent with the directions of the neighbouring faces to avoid ugly edges. So a good way to ensure this is to line them up with the UV texture coordinates of the model. These other two vectors are called the tangent and the bitangent. The way that we're going to get these two vectors is to calculate the tangent based on the UV texture coordinates when the model is originally loaded, and we'll then store these tangents in the model's VAO, just like we do with the normal vectors. These will then get passed to the vertex shader as vertex attributes, again just like we do with the normals, and the bitangent can then be calculated per vertex by simply taking the cross product of the normal and the tangent vectors. Using these three vectors will create the matrix, and this will then be used to transform the camera and the light directions into tangent space. The fragment shader won't look much different from usual, with the only difference being that the normal vector comes from the normal map instead of the vertex shader, and the lighting calculation is then carried out in tangent space. For this tutorial, I didn't really want to implement normal mapping using our current entity rendering system, because that would have meant that you'd need to swap out all of your current models for models with normal maps. So instead I thought I'd create a brand new rendering system just for normal mapped entities, and then you can choose which models get rendered with normal maps and which don't. So I've created a new rendering system for entities which you can download from the description of this video, and that's what we're going to be using in this episode to implement normal mapping. I've also provided a new OBJ loader which you also need to add to your source folder as well, and this updated OBJ loader calculates the tangent vectors for each vertex. The way that I calculated these tangent vectors for each triangle was using this formula here. I'm not actually going to take you through the changes that I made to the OBJ loader in this tutorial, because there was quite a lot of just general Java programming involved, and this tutorial is already going to be pretty long, but feel free to have a look at the changes I made and ask me about them, and I've also provided a link in the description to explain the maths behind this formula. The way that this is implemented will be different for each OBJ loader anyway, but the only new thing that you'd actually need to know is the stuff on the screen right now. So just copy those two packages into your source folder and refresh the source folder in Eclipse so that you can see them, and then just have a quick look through the new rendering system. You'll see that at the moment it's pretty much identical to our usual rendering system, with just a couple of tiny things added in or taken out for convenience, but there's absolutely no new stuff in here at all. The only real difference is that the lighting calculations in the shaders are now done in eye space, so that's relative to the camera rather than to the world, just to demonstrate that you can carry out the lighting calculations in any space and you'll still get the same result. So in the vertex shader you can see that the light direction and the camera vector are now calculated based on the vertex position relative to the camera, and the light positions are actually pre-multiplied with the view matrix in the shader class, so that they're already in eye space in the vertex shader. The first thing that you might notice is in the normal mapping renderer you may well have an error where we're accessing the colours from the master renderer, and that's because if you have a look in the master renderer I've currently got them as private, so change them to public if you haven't already. Now in the master renderer we need to set up a few things to get this normal mapping renderer process all set up and running so that we can use it. So we're going to create a new normal mapping renderer, and we're going to initialize that in the master renderer constructor. So create a new instance of it, and this is going to take in the projection matrix. So let's put that in here. Before we forget, let's go down to the cleanup method and call the cleanup for the normal map renderer so that everything gets cleaned up when the game closes. Also, we're going to need to have a new hash map of entities specifically for the entities that are going to use this new normal mapping pipeline for rendering. So create a new hash map. And we're also going to need a new process entity method, so copy and paste that, and this new one is just for the normal mapped entities, so give it a new name and change entities to normal map entities, or whatever you called the hash map for the normal mapped entities, and you've got to change that twice there, so make sure you do that. Then the render scene method, if you've got one, needs to take in a list of entities, a new list of entities, which is going to be the normal mapped entities, and then every single frame we need to loop through those normal mapped entities and process them all so that they all get added to that hash map. So if you don't have a render scene method, this would need to go in the main game loop, in the while loop. And once you've processed all of the normal map entities, they'll get sent off to be rendered, and in the render method we actually need to render these normal map entities, and we can do that very simply by calling normal map renderer .render. That takes in the normal map entities, the clip plane, the lights and the camera. And very important, we need to remember to clear the hash map of normal mapped entities after rendering, so definitely don't forget to do that. Then in the main game loop class, we need to create a new list of entities specifically for these normal mapped entities, these entities that are going to use this new rendering pipeline, and create a new array list, and that needs to be given to the render scene method every time we call it, which if you've done the water tutorials will be 3 times, so put that in as the second parameter each time. You'll now need to create some entities that you want to render with normal mapping. So you can see here that I've created a new textured model using the barrel model and texture, which you can download from the description of this video. You'll also notice that I've loaded the barrel model using the new normal mapped OBJ loader, which you must do if you want to render it using the new normal mapping rendering process, because that OBJ loader calculates the tangents, which are absolutely necessary for rendering with normal maps. I've also made the barrel texture a little bit shiny, which will show off the normal mapping nicely when we've implemented it. And then you just need to create some entities and choose a position in the world where they'll definitely be visible. And then you just need to add them to the normal map entities list so that they get rendered using the new rendering process. So make sure you add them to the correct list of entities there. Once you've done that, you can just run it to test if it's all working. And right now you should just be able to see your object rendered as usual in the world. So let's now get started with actually implementing normal mapping. In the loader class, you're going to need to create a new load to VAO method so that we can also load up tangents to the VAO so that we can access them in the vertex shader. So this takes in a new parameter, which is a float array of tangents, which we're going to store in attribute list 3. So this first parameter needs to be a 3. Second one, they're 3D vectors, so that doesn't need to change. And the third one, we put in the float array of tangents. Then we need to go into the new normal mapping OBJ loader, and in the load OBJ method down at the bottom, we're calling the load to VAO method, and we need to call the new load to VAO method by putting in the tangents array, the array of these tangents, into the load to VAO method so that it gets loaded up into the VAO, which we can access in the vertex shader. Before we render, so in the normal mapping renderer, before we render, we need to enable that attribute list 3, and after rendering, we need to disable it again, so called disable vertex attribute array 3. In the vertex shader, we need an input for the tangent so that we can access it, and that's going to be a vec3, and we need to link up that variable with the attribute list 3 of the VAO, and we can do that by calling bind attribute 3. We want to bind to the tangent variable, which we've just created in the vertex shader. Nothing that we haven't done before many times. Now what we're going to do very quickly in the vertex shader is we're just going to pass the tangent straight to the fragment shader so that we can output it and have a look. So create a new out vec3 called pass tangent and set that to the tangent. And then in the fragment shader, we're going to need an in vec3 pass tangent, and then we're just going to set the output color to that tangent so that we can check everything's working. So out color equals, and we need to make it a vec4 because out color is a vec4. So pass tangent and then a 1, and it should look something fairly similar to this if it's all working. If it hasn't worked, then you need to go back and check what's gone wrong, because it's not going to work if this part hasn't worked. So make sure that you've got to this stage before continuing. So if that'll work for you, then you can get rid of those last few lines that we added. So get rid of setting the out color and get rid of the pass tangent in the fragment shader, and in the vertex shader you can get rid of the 2 lines with the pass tangent as well. So let's now concentrate on the normal map itself, and in the model texture class we're going to add the possibility for each texture to have a normal map associated with it, and we're also going to create a getter and a setter for the normal map, so you can set a normal map to a texture if you want to. It's an optional thing. Then if we go back into the normal map vertex shader, we no longer need to output the surface normal. That's going to be calculated in the fragment shader, but we do still need to do this calculation here, so let's declare the surface normal as a vec3. Then in the fragment shader, we obviously no longer need to take in a surface normal, and this line here we're going to change in a minute, so don't worry about that just yet. What we do need is a sampler to sample the normal map. So create a new uniform sampler 2D for the normal map, and the first thing we're going to do obviously is to sample that normal map to get the value of the normal map. So we're going to sample it using the texture function. We're going to sample the normal map, and we're going to sample it at the usual texture coordinates. And as I mentioned earlier in this video, we need to do that quick conversion to make sure that all the components of the normal are between -1 and 1. So we can now use that to create the unit normal, and obviously we only need the first 3 components, the RGB components or the XYZ components, and that will get normalized to be the unit normal vector of this fragment. And for now we're just going to test this by outputting the normal map value as the output color of the fragment shader. Now in the normal mapping shader class, we need to do the usual thing for that new uniform variable that we've just created for the normal map sampler. So get the location of it, and then we also need to indicate which texture unit it should be sampling from, and we can do that by loading up an int to it. So in the connect texture units method, we're going to load up an int to the normal map sampler to indicate which texture unit it should be sampling from, and we're going to be sampling from texture unit 1. So we also need to remember to bind the normal map to texture unit 1. So let's do that in the prepared texture model. So copy those 2 lines. We're going to bind, we're going to make texture unit 1 the active texture unit, and to texture unit 1 we're going to bind the normal map associated with that model. So in the main game loop, we now just need to associate a normal map with that barrel model that I've set up to use the normal mapping rendering process. So we're going to do barrel model.getTexture.set normal map, and I've got a texture called barrel normal in my res folder, which you can actually download from the description of this video. And then if you run that, it should get mapped to the surface of the barrel, and you can see that that is working quite nicely here. So make sure that that's working for you, and if it isn't, stop here and go back and try and work out what's gone wrong. So if that all worked for you, then you can go back into the fragment shader and get rid of that last line, which we were just using for testing. And now we're going to go into the vertex shader, and we're going to create that matrix that I was talking about earlier that can transform the directions into tangent space. And as we talked about earlier, this needs 3 vectors which define the tangent space. First, it needs the up vector, which, as we said earlier, is just the normal. So that's just the surface normal. The second vector that we need is the tangent, which we're getting as an input to the vertex shader. But what we need to do is to transform that tangent into I space first, because we're trying to transform everything from I space to tangent space. So these vectors need to be originally in I space. So let's transform the tangent that we're getting as an input into I space using the model view matrix, and put brackets around this whole thing and just get the XYZ components, because the tangent is just a 3D vector. And then finally we need the bitangent, which we can get by taking the cross product of the normal and the tangent, and that will return a 3D vector which is perpendicular to both the normal and the tangent. Now we just need to make sure that these 3 normals are unit vectors, so put brackets around everything and normalize the whole thing, and be careful with the brackets here. You want to put brackets around the whole thing for each of these. So we're going to normalize each of these 3 vectors, making them all unit vectors, and then we can use them to create this matrix. I'm going to put a link in the description explaining why this is the matrix and why this works. But for now, just create the matrix like this. So the first row of the matrix needs to be tangent x, bitangent.x, and normal.x, and I'm just going to copy that because the next line needs to be tangent.y, bitangent.y, normal.y, and the last line, as I'm sure you've guessed, is tangent.z, bitangent.z, and normal.z, and then get rid of that last comma. So we've now got a matrix which can convert from I space to tangent space, and that's what we're going to do for the light vector here. So put a bracket around everything and multiply it by the toTangentSpace matrix to convert it into tangent space, and the same for the to camera vector. We're going to convert that from iSpace into tangent space, and that should now be it, because everything in the fragment shader can stay the same. That lighting calculation will now be done in tangent space. So if we run that, if everything has gone well, you should now have some working normal maps, and as you can see here on the barrel, the normal maps are now working pretty nicely. The only slight problem is that mip mapping can sometimes ruin the effect and make everything a bit blurry sometimes, and you can fix that temporarily by changing the bias in the load texture method. If we make this more negative, then the mip mapping is less severe, but it also makes everything a bit slower because the textures are now being rendered at a much higher resolution. But this will actually all be fixed when we cover anisotropic filtering, which we will do soon. So that is it for this week. If you'd like to help support this series, then you can check out my Patreon page, which I've linked in the description. And we've actually already reached the first milestone goal, which means that you're now guaranteed tutorials at least every 3 weeks. And it's actually not too far off the next milestone, which would allow me to definitely be able to make tutorials at least every 2 weeks. Which is great, because I thought I'd have to get a full-time job and would hardly have any time for making these videos. But if the Patreon keeps going like this, then that may well not be the case after all. Next time we're going to be working on either particle effects or text rendering, and that video should hopefully be out in 2 weeks' time. If you have any questions about this tutorial, then do leave a comment or send me an email, and I'll do my best to explain things further. But yeah, thank you guys very much for watching this video. Do subscribe if you haven't already. Have a brilliant week, and I will see you all next time.